Hello, dear friends. This is Mechanical Vibration Lecture 9. It is our self-excitation and the stability analysis. So this is the continuation of previous lecture. Okay, so this self-excitation and stability analysis more concern one of an important topic of vibration analysis. So the force acting on a vibrating system usually external to the system and independent of the motion in most cases. But in some cases, there are systems for which the excitation force is a function of the motion itself or the motion parameter itself. So mainly the motion parameters include displacement, the velocity and the acceleration of the system itself. And such systems are called self-excited vibrating systems, since the motion itself is produces the excitation force. So the instability of rotating shaft and the fluttering of the turbine blades and the flow-induced vibration of pipe and the automotive wheel chimney and also the chimney and aerodynamically induced motions of wheels are some examples of self-excited vibrations. Dynamic stability analysis. The system is said to be dynamically stable if the motion is converged. Means in most cases there are some cases in which motions is diverge, and in some cases the motion will converge or sometimes remain steady with time. So the case where when the motion converges or remain steady with time, then it is called dynamically stable system. And on the contrary to that, when the motion is diverge with time, then we call it as dynamically unstable system. The motion diverges and the system become unstable if energy is fed to the system through self-excitation. So let's see some circumstances that leads us to instability. Let's consider the equation of motion of single degree of freedom motion system. This is a question of motion of single degree of freedom system with no external force. Means what we are talking is the external force is derived from the system motion itself in the case of self-excitation. So because of that, this equation is a free vibration equation of single degree of freedom system. Now, if we assume solution for this, that x of t is equal to a e s t, and c is a constant that will be found from, it is c, not c, but this a is amplitude, maximum amplitude constant. And then when we substitute this equation into this equation, instead of acceleration, instead of velocity and displacement, then finally we get this equation. Okay, so m is a mass, okay, c over m, k over m, which is equal to 0. And this is a quadratic form of equation for which we have a quadratic roots s1, which is equals to this equation, okay, which is c over minus c over 2m plus or minus half radical c over m square minus 4 k over m. So this is a quadratic form of equation. So the solution is assumed to be x of t, which is equal to a est. That means we use exponential relation here. The motion will diverge and aperiodic if the root s1 and s2 are real and positive. This situation can avoid if c over m and k over m are positive. Okay, so the motion will also diverge if the root S1 and S2 are complex conjugate with positive real parts. So for that, to analyze the situation, let's root S1 and S2 of the equation 3 here be expressed as S1 is equal to P plus IQ and S2 is equal to P plus minus IQ. This complex conjugate form of representation. Okay, the roots, complex roots. Now, where P and Q are real numbers, so that S minus S1 times S minus S2, which is equals to, this means what? S square minus S1 plus S2 S plus S1 S2, which is equal to S square C over M S plus K over. So this relates, directly relates with this equation as, okay, here S square C over M is equal to S1 plus S2, okay, and K over M is equal to S1 S2. So that is the relation. C over M is equals to minus of S1 plus S2, this part, which is equals to minus 2P with the previous relation. K over M, this relation is S plus S1 S2, which gives P square plus Q square. So this equation number 6 shows that for a negative P, C over M must be positive, and for positive P square plus Q square, the K over M must be positive. Therefore, the system will be dynamically stable if C and K are positive, assuming that M is always positive. So let's take some example in order to analyze the self-exciting system. We consider equation of motion of single of degree of freedom motion that mx dot dot plus cx dot plus kx is equal to f of t. Now let's derive the condition that leads to divergent oscillations. Means that is instability situation, in which one of the case when the forcing function is proportional to displacement, means f of t, the forcing function f of t is proportional to displacement f naught x of t. F naught is some constant, and x of t is the disturbance from the system itself. So the self-excitation is because of the displacement parameter, because most of the self-excitation comes from the system parameters. So now this is the first case. Another second case, when the forcing function is proportional to the velocity, okay, f naught x dot of t. So instability is result from due to velocity. And the third case is when f of t is proportional to the acceleration of the motion. So these three conditions will help us to analyze the self-excitation system. Okay. So now the question, let's consider the first case, first case, when the forcing function is proportional to displacement. So this indicates f of t. The forcing function f of t is equals to f naught x of t. Now the equation of motion becomes mx dot dot plus cx dot plus kx is equal to f naught x of t. Now, after rearranging this thing, it becomes mx dot dot plus cx dot plus k minus f naught x is equal to 0, because these parameters are the same parameters. So this is equation of motion for this case. And assuming the x of t is equal to the solution x of t is equal to c times est. C is the amplitude constant, okay, that should be determined. And then the velocity and the acceleration becomes sc e to the power of st, x dot dot of t, which is equal to s square c est square est. So these are acceleration velocity and displacements. So substituting on the previous equation, we can get this relation, and that it gives us the quadratic form of equation. Okay, so this quadratic form of equation will be solved using the quadratic equation. So that would be minus c over 2m plus or minus radical of c over 2m squared, the whole, minus k minus f naught over m. So this is what we have. Now here's, we can consider it in many ways. First, consider the case of positive stiffness. Now, k minus f naught greater than 0 means this is stiffness term. So k minus f naught over m, we consider this part. This implies k greater than f naught. Okay. So yeah, for positive stiffness case, we have again 3 cases in this only. That means c over 2m square, the term inside the radical, which is c over 2m square minus k minus f naught over m greater than 0 case. In this case, both S1 and S2 will be real and negative. Hence, the solution will be x of t is equal to C1 ES1 t plus C2 ES2 t. So this is both S1 and S2 are real and negative case. This shows that the system is stable. In this case, the system is considered stable. Another case is the term inside of radical equal to 0 means c over 2m minus k minus f naught over m is equal to 0 means c over 2m squared is equal to k minus f naught over m. In this case, both S1 and S2 will be identical. We can, because the inside the radical term is equal to 0 means we have left only this term. Only this term left. So S1 and S2 are having the same values. Okay. So during that time, the equation becomes x of t is equal to C1 plus t C2 ES1 e the power of S1t. So this shows the system will be stable since as t approaches to infinity and e raised to S1 times t approach to 0. And the third case under this condition is c over 2m square less than k minus f naught over m. So during this time, both S1 and S2 will be complex conjugate form. Hence, the solution will be x of t, which is equal to c times e raised to minus c over 2m t sine of radical distance. Okay, so this shows converging oscillation motion, and hence the system will be stable. For the negative stiffness case, the second case is negative stiffness case. So that means k minus f naught less than 0. So k is less than f naught. Here the roots are S1 to which is equals to minus c over 2m plus or minus radical of c over 2m square plus f naught minus k over m. So these are the two roots. Therefore, S1 will be positive and S2 will be negative. And the solution becomes x of t is equals to C1 times e raised to plus S1 t plus C2 raised to minus S2 t. This solution can be seen to diverge as t approaches to infinity. The second case is when the forcing function is proportional to velocity. So the self-excitation comes due to the presence of velocity. So f of t is equal to f naught x dot of t. So in this case, our equation becomes mx dot dot plus cx dot plus kx is equal to f naught x naught x dot of t. Therefore, mx dot dot plus, which implies mx dot dot plus c minus f naught x dot plus kx is equal to 0. And also, assuming similar solution as the previous, we have this relation that s square plus, this is not s to the power of s, but it is s square plus c minus f naught over ms plus k over n, which is equal to 0. The quadratic roots S1 and S2 of these equations are, we have these quadratic roots. S1 and S2 are minus of c minus f naught over 2m plus or minus radical of c minus f naught over 2m the whole square minus k over n. First, consider positive damping. Now, what we are talking is the damping. In the previous case, what we discussed is about the stiffness. Okay, now it is about the damping. So, considering positive damping, so that means C greater than F naught, the system will stable for all possible values of this C over F naught over 2m the whole square minus K over n. Next, consider the case of negative damping. That means C minus F naught less than 0, means C less than F naught. Depending on the sign of quantity under the radicals in the above question, we will have three possibilities. Okay. The first one is C minus F naught over 2m squared greater than K over m. Okay. Here, S1 and S2 are real and positive. So we have this equation. This is the solution of the differential equation. This shows a diverging non-oscillatory motion, so that the system is unstable system. The system is unstable system. So the system is unstable system. Case 2, C2 minus F naught 2m the whole square, which is equal to K over m. In this case, both S1 and S2 are identical, means we have only one root